All right. So I can't remember if I showed you last time these the shape of these orbitals, right? This is our p orbitals. Our p orbitals, dumbbells, are labeled px, py, and pz. Let's see, Aisha, are you there?
Yes, Dr. Scott.
Did I show you guys this last time, the px, py, and pz?
I don't think so.
Okay. So we talked about the shape of the orbitals, dumbbells, and their names are px, py, and pz. But remember that they will be, I mean, the atom nucleus isn't maintaining its trajectory generally. It depends on how it's bonded and so forth, but it'll be spinning all over the place. Therefore, these would be spinning as well. Did you have a question, Joey, or just coming in?
I was just coming in.
All right. Okay, so our d orbitals, these are the shapes of our d orbitals and their corresponding names. And we're not going to talk about why they're this shape. And I think last time I led you to believe that the shape of the d orbital was just the same as the p. It's like there's two p's overlapping in most scenarios. And then this is the trace that the wave function for the fifth d orbital is. And the names of these d orbitals, dxy, dxz, yz, x squared minus y squared, have to do with the planes that that they are in. All right. Now we're going to talk about some of the physical properties of atoms that we can know now that we understand the electron configuration and the orbital diagrams. Okay. One of these properties is what we call, well, has to do with the ability or the easiness in which an atom will lose an electron. All right. So we talked about how the higher the n value, the more energy the electron has, and also thus the easier it is for that electron to be removed. Let me close this door behind us here. Okay. So the higher the n value, the easier it is to remove an electron. And the reasons, there's a couple of reasons why that's the case. And I think that, I know that we've talked about these briefly. Let me get a good pen here. But let's kind of go over them. First of all, the distance is probably the major contributor as far as why an electron is going to be removed. We'll use our planetary model here to help us understand things. But we also have electrons below the electron in question. So if we're talking about this electron and how easy it is to remove it, we have something that's called shielding. Because below this electron, there are other electrons which kind of shield this electron from getting the positive charge attention. Right? I kind of use it as a model like these are the parents and the electrons are the kids, right? The farther the electron is from the kid, or sorry, the farther the kids are from the parents, the less attention they get. And if you think about maybe a family walking through the mall, and I just know this because whenever I take my family through the mall, right, when we had 6 little kids running around and we would be walking down the mall, the range that we took up, the amount of space that we took up was large because the 6 kids would be kind of moving all around and they'd be hard to kind of encourage to walk close to us. And so we would say, come on over here, don't touch that, stay away from there. And they would kind of cluster around us for a while, but then they'd roam out again, right? If we had 2 parents, then it was easier to kind of keep all the kids together. If we had 2 less kids, right, only 4 kids compared to 6, for example, then it became easier to manage the kids, and the electrons would actually, or the kids would actually be closer, okay? And this is the way the atom is as well. Because as the number of protons increases, what we call the effective nuclear charge increases, right? So the more positive charges you have here, the more the electrons will be brought in towards the middle. Okay? And if there's fewer electrons on the outside, then there's more positive charge to go around. Again, the electron will decrease, or sorry, the atom will decrease in size. Okay? Now, a reminder, I think I mentioned this last time. Did you have a question, Anastasia?
Oh, sorry, no.
Okay, all right. One thing that I mentioned, or that I'm not positive I mentioned, but I think I did, but the size of an atom relates to the furthest electron, right? Now, if we go back to our kind of our p orbitals, for example, oops, and we talk about, trying to determine how big this atom is. How big is this atom, right? If I took this thing and started spinning it in all directions really fast, it would really look like a sphere. Can everybody understand that? Does that make sense? Because if this is spinning around like a fan would spin, you'd have blades on a fan, right? And if these were spinning, this would really manifest itself as a kind of a disc, right? You would see this, and no matter where you put your finger in there, it would be cut by the fan. It's the same thing with this atom, right? This thing is spinning around, so essentially it would look like a sphere, and wherever you put your finger in, the first thing you would touch would be these edges. Does that make sense, Alyssa?
Yes.
Okay. So the idea is that the size of the atom is associated with the furthest electron, the electron that's farthest away. Its orbital would be spinning around, and that's what the size would be related to. Okay? So,
I have a question.
yeah.
So, these bigger atoms with, very large protons, are they still relatively bigger even though they're holding their electrons closer?
If you have, for example, mercury, 80 protons, compared to something like zinc, only 30 protons, the nucleus itself doesn't even, influence directly, at least, in terms of the size of the nucleus, and that's something that nobody really talks about in chemistry. So here's a zinc nucleus, for example. You would say, oh, mercury is much bigger, has a lot more nucleons, whoops, Hg, here's zinc. Yes, that nucleus is larger, but the size of the atom, again, doesn't relate, it's not because of the nucleus, so to speak, right? We know that mercury is going to have 80 electrons as well, and those electrons are going to be out here and result in a large atom indirectly because there was 80 protons, therefore there's going to be about 80 electrons, right? So the size in some way kind of does relate to that, but it's not because the nucleus is necessarily bigger itself. Okay? Do you remember our model of if we had an atom and the nucleus was the size of our computer screen? The first electron, does anybody remember where the first electron would be? How far away it would be if I had an atom nucleus that was on my screen that was, about this big. We saw it a long time ago, but the first electron, first one, I think it was like 23 blocks away, right? So miles away from us, the first electron would be. Does that make sense? So even if I quadrupled the size of this, the distance of the electron wouldn't be influenced because the first electron wouldn't be influenced. Does that answer that question, you think?
Yes, thank you.
All right. So then we have this chart showing us the size of atoms, the size of atoms, and our new understood knowledge as far as how the electrons are filling in atoms and orbitals can be used to explain these differences in sizes. So if you look at something like lithium here, All right. It's not surprising that sodium is larger. Lithium, I'm going to write the electron configuration for lithium. 1s2, 2s2, whoops, 1s2, 2s1. There we go for lithium. But for sodium, 1s2, 2s2, 2p6, 3s1. Right? So it shouldn't be surprising to us that sodium is larger than lithium. See, lithium here we have 152 picometers, and let's see, are these in? Yeah, picometers there, volume picometers, and sodium 186 picometers. All right, that's not terribly surprising because we have our 3s shell, our third shell, that is added on to bring in sodium, right? I mean, if we want to bring in electrons for sodium, we have to go into the third shell. So we have a larger atom, all right? So coming down the periodic table, the atoms get larger. However, moving left to right, lithium, electron configuration 1s2, 2s1, compared to beryllium, electron configuration. Anastasia, what's the electron configuration for beryllium? What do you think, Anastasia? What's the electron configuration for beryllium? Are you there? Brielle, what's the electron configuration for beryllium?
1s2 and 2s2?
That's right. 2s2. 1s2, 2s2. Okay? Now, compared to lithium, 1s2, 2s1, the extra electron is only going into, and we can kind of draw these. Here's our nucleus. There's our 1s, right? It has 2 electrons in it. And then we have our 2s. Lithium has 1 electron in it, right? This is our 1s. This is our 2s. But beryllium just has a second electron in the same subshell, all right? So it wouldn't make sense for that atom to be bigger because it's in the same subshell. And in fact, it's getting smaller. Any ideas why beryllium might be smaller than lithium, Camilla?
I see why they'd be the same size because they're in the same subshell, but I'm not necessarily sure why it would be smaller.
Okay, so what's happening is beryllium is actually gaining a proton. And so because we have another proton in there, the electrons contract down and the size is slightly smaller as you move from left to right across the periodic table. All right, so it's going into the same shell, A, like you mentioned, and then B, you're increasing the number of protons, so there's a stronger positive charge pulling them in. Kind of like parents. Yeah, go ahead, Chloe.
You said that like the more positive it is, it'll decrease its size. It gained a proton, but didn't it also gain an electron? So shouldn't that just like cancel it out? Because it's like negativity also added to it?
To a degree, but that electron that it's gaining isn't going in a different higher orbital. It's going in the same place. So because 2 electrons can reside in a 1s or an s orbital, and you can see the same trend follows, for example, from aluminum down to argon. 6 electrons can reside in this orbital. What orbital are these electrons in? Let's see. Was it Camilla's turn? Did I already ask Camilla a question?
You already asked me.
Oh, go ahead. What is it? What electrons are we filling up here? Or what orbital, sorry? Aluminum to argon. What subshell are we filling when we're putting electrons in from aluminum to argon?
I don't know.
Okay. What is this block over here?
The P block?
That's the P block. And because we're in the what row or what N value? Aluminum to argon? No, it's 3 actually, right? 1, 2, 3.
Oh, yeah.
Did I say N value? Well, yeah. So it's L value is 1 here, but N value is 3. So this is our 3P subshell that's being filled from aluminum to argon. And because it's a P subshell, we know that 3P looks like this, and you can put 6 electrons, and all of them are going into, let me try to draw these, right? Going into one of these 3p orbitals to start with, and then they're pairing up. And so we're not getting larger, we're actually decreasing, because every time we increase the atomic number, we're also increasing the number of protons by 1. Okay? All right then. So that's our trends, right? Our atomic trends. So, a common question is, what's a larger atom? What has a larger radius? Hydrogen or helium? Now, it's kind of hard to tell with our plot here. I'll make it smaller so it's even harder to tell. But based on our understanding of how our periodic table works, what do you think, Chance? Based on our understanding of how our electrons go into atoms, what's larger, an atom of hydrogen or an atom of helium?
Is it atom of hydrogen?
That's right. An atom of hydrogen is larger. And why would we say that's the case, Chloe? Why would an atom of hydrogen be larger? Or maybe we should say, why should the helium be smaller?
The
Helium's smaller because it has another proton.
So
That's
it's more
right.
positive.
That's right. Another proton. And, another way to say that is it has a larger effective nuclear charge. Another proton is just perfect. Very good. Now let's talk about ions. And I want to keep our analogy going a little bit at least. If I'm in the mall and I have 3 kids but 3 adults, then the kids don't run very far away, right? If I go to the mall, though, and I have, let's say, my wife and I, and we have our 6 kids, but then let's say 2 kids brought friends. So we have 2 additional kids. What do you think in terms of the area that we would take up in the mall? Would you think it would be more or less, Daisy?
Well, since you have more kids, it makes me want to say that you'd be less. But I feel like you are at an extent where you have so many. I don't know. I feel like my first guess would be less.
Less space if we had 2 friends?
It would take less space, yeah.
Yeah, well, it's just a story, so it doesn't matter if you didn't understand the story. But the idea is, when you bring kids to the mall, your own kids, they respect you a little bit. But then when you bring friends, that respect goes out the door, right? And they just start running off with their friends like crazy. So, here's me, here's my wife, here's our 6 kids wandering around. That's our shape. If you have you and your spouse and then 2 extra kids, then the space is going to be much larger. And it's the same thing with ions. So here you see we have the oxygen atom, very small. You can look at any ones in here, either the oxygen atom, sulfur atom, selenium, beryllium, right? And then their respective ion. The ion, because it has how many more electrons, Eleanor? The sulfur ion, how many more electrons does it have? Eleanor, are you there? Emily, are you there? Emily? Falata? Emily's there. How many extra electrons? So here's sulfur atom. It's smaller than the sulfur ion. How many extra electrons does that sulfur ion have?
2.
2. 2 extra electrons, that's right. and that increases its size dramatically, right? You can see oxygen very small getting very large, right? And notice how chlorine increases in size, 1 extra electron, but notice the relative size between chlorine and chlorine ion, and the sulfur ion, right? Not a huge difference there, even though chlorine only gained 1 electron, okay? All right, so what about cations? Falata, what do you think? Here's a cation, calcium. Why is calcium ion so much smaller than the calcium atom?
Because it's gaining electrons.
It's gaining what?
Electrons.
Well, calcium atom here going to the calcium ion, right? It's not gaining, is it? It's doing what?
Proton.
Well, it hasn't gained or lost protons, right? But it is losing electrons, but it has the same number of protons. So when it loses electrons, but has the same number of protons, then your resulting ion is going to be smaller. All right? Very good. So that is how we understand why our trends follow the way they do. And it's our orbital diagram, our electron configurations that help us understand that better. All right. So take a look at this. Joey's going to tell us the answer in about 40 seconds. You guys work in your own minds. Make sure you work for it. Try to get an answer. Don't just let it rush it by. All right, which one is correctly compares these? You ready, Joey?
I think so.
All right. What's the answer?
I think it's A,
A?
because when you lose electrons, like what magnesium is doing here, then the resulting ion is smaller in size.
Okay, very good. Here, oxygen is gaining electrons, so it would be larger. Neon and magnesium. Let me bring up my periodic table. Where's my periodic table? Wait, do I have? Oh, I got a new computer because my old one wasn't handling things, and I don't think. Where is it at? Holy mackerel, piece of junk. All right. Anyway, I'll get a periodic table from the drawer here. Looking at magnesium and neon. Magnesium and neon. So why is neon smaller than magnesium? What's our explanation for why neon is smaller than magnesium? Catherine Blackburn. Why is magnesium smaller than neon? Or sorry, is that right? No, why is magnesium larger than neon?
I would say because
Is
because magnesium has more protons, but wouldn't that make it smaller?
Like,
You don't actually know why.
All right. Very good. So you're right. Magnesium would have more protons, and so we would expect, and we might think, well, he just said that the more protons, the smaller the atom. However, when you go from neon to magnesium, the electrons are no longer in the second shell, but they have to be where to go into magnesium here?
Oh, because it goes into a third shell, so it has another layer, I guess.
That's right. That's right. Another shell. And so that extra shell is in a different location, so the atom is going to increase. And that's what we see. As you move down the periodic table, you get an increase in your atomic size. Okay, very good. So,
I have a question.
yeah.
I'm just confused because can you go back to the last slide?
This one?
Yeah.
Mm-hmm.
So I just thought when we were talking about DA earlier, and we were talking about how it lost electrons and it had the 2 plus and that made it smaller. And so now I'm confused why that's correct. That Mg is bigger.
So what did you just say? You said that beryllium, or are you talking about barium? Which one were you talking about?
Calcium.
Oh, calcium. So calcium,
Yeah.
if calcium loses electrons,
Mm-hmm.
I think maybe if we go back to this one here. If calcium loses electrons, so this is calcium, and this is the calcium ion, right?
Mm-hmm.
It lost electrons, so the calcium atom is larger than the calcium ion. True?
Yes.
Okay. So this is saying that the magnesium atom is larger than the magnesium ion.
Okay.
So we're looking for the one that's correct.
Okay.
Okay. So, takeaway message. Positive ions are always smaller than their atoms, while negative ions are always larger than their relative atoms. Okay? Another property, physical property, which is relatively easy to measure, is what we call ionization energy. It's the energy associated with making an atom an ion. All right? Now, if you think about this same analogy, kind of the nucleus being the parents and the electrons being kids. Now, this is sometimes a little bit of an uncomfortable analogy, but I think it helps people understand what's going on. If you have somebody trying to take one of your children away, it's going to make the parents unhappy, right? It's going to aggravate them and raise their energy level. And so it will always require energy to remove an electron from an atom. Okay, can everybody kind of imagine that? It's always going to require energy to remove an electron from an atom. Now, sometimes it requires a little bit less energy, right? And why is that? Well, here's helium, nice little family, 2 nucleus and only 2 kids. If you want to remove an electron from helium, it's going to make the atom very mad because it doesn't want to lose any of its kids. Whereas down here, we got something like francium, 87 kids, right? Yeah, it's nice and it likes all its 87 kids, but it really is less affected if it loses one of its 87 kids. All right? So, not a very comfortable analogy maybe, but hopefully helpful to recognize that it will always require energy to remove a child, an electron, from an atom, from a family. But the more electrons that it has, then the less energy it's going to require to remove that electron. Okay? Also, what we have are called successive ionization energies. Now, I should have a little bit of a conversation about this term ionization energy. This is a poor term in my opinion because in terms of the energy associated with creating an ion, if you're talking about the energy associated with creating an ion, you could be creating an anion and then giving an electron. And so that's, in my opinion, ionization energy is a poor phrase. It should be cationization energy because they're talking about taking an atom and removing an electron, always forming a cation. Okay? And we kind of have to remember that. It's not going to be called cationization energy, but it should be called cationization energy. And if you can always remember that, then you'll always remember that this is the energy associated with removing an electron from an atom. Now we have what are called successive ionization energies. And that means Not just removing one electron, but removing a second, a third, and a fourth, and so forth. All right? What do you think? Do you think it's going to take more energy to remove a second electron than it is the first? Whose turn is it? Kylie Johnson, can you answer that? Do you think it's going to take more or less energy to remove a second child from a family?
More.
More, that's right. And that's the way it is. Every electron that you remove, it takes more than the previous one. All right, more than the previous one. And we'll see some trends here in terms of just removing one electron. Here it is to just remove one electron. And you can see, looking at helium, requires a lot of energy to remove an electron. Moving down to radon, right, it decreases the amount of energy required to remove that electron. All right, so we have ionization energies that decrease as you move down the periodic table in general, increase as you move to the right. All right, and that's, you know, you might say, well, why does it increase as we move to the right if they're getting more kids? Well, that is answered by our orbital diagram, right? So why do you think it takes more energy to remove an electron from neon than it does to remove an electron from fluorine, Rebecca? Why does it take more energy to remove an electron from neon compared to fluorine?
Because it wants to keep its electrons more.
That's true. That's true, but why? Why does fluorine have a stronger attraction to that electron? Sorry, neon have a stronger attraction than fluorine. Okay, so we're going to try to... Falata, do you want to put your microphone on mute? So let's answer this using our orbital diagram. Our orbital diagram, right? What do you think, Rebecca? Any ideas based on the orbital diagram?
I'm still kind of confused with the orbital diagrams, not gonna lie, so...
All right, so let's try to draw one then. Here's our orbital diagrams. This is the energy associated with that. Okay, so the energy associated with removing electrons from neon, or well, this is our energy for our orbital diagram. Electron configuration for neon, let's write it up here. 1s2, 2s2, 2p6. Did I do that right for neon, Rebecca?
I think so.
All right. What's fluorine's then? Fluorine is what?
1, 2.
Mm-hmm.
2s2 also.
Uh-huh.
And then 2p5.
2p5. That's right. 2p5. Okay. So, if we're removing an electron from fluorine, where is that electron going to come from? Is it going to come from the 1s2s, the 2s2s, or the 2p5s?
The 2p5?
That's right, the 2p5. So let's draw the 2p subshell. And let's fill it up with 5 electrons. 1, 2, 3, 4, 5. Okay. I'll also draw the 2p subshell for neon and fill it up. 1, 2, 3, 4, 5, 6. Okay.
Okay.
So, looking at these, can we make an argument for why it requires more energy to remove an electron from here compared to here?
Because neon wants to keep its full subshells, and fluorine would not be... Like, getting rid of one would make it more stable.
Well, getting rid of one, it's already has a degree of instability there, right?
Mm-hmm.
So getting rid of one here wouldn't make it as distable as breaking up that complete subshell. Good. Very good. In fact, if we look at the electron or the ionization energies, again, the energy required to remove an electron from an atom for boron, carbon, nitrogen, oxygen, fluorine, neon, why do we see a dip when we go from nitrogen to oxygen? Why do we see a dip there when we go from nitrogen to oxygen? What do you think, Sarah? Are you there?
Yes.
All right, so let's draw our electron, or I don't know, do you already understand, have an idea for the answer? Why does oxygen require less energy to remove an electron than nitrogen?
I'm
I'm
not
not
sure.
sure.
Okay, so we have to draw our orbital diagram for the two atoms. Okay, so let's draw an orbital diagram for oxygen here and one for nitrogen. Are you okay drawing the orbital diagrams, or is that difficult as well?
Yeah,
I
I get
get
that.
that.
Okay, great. So, what subshell are we looking at when we're talking about oxygen here? What subshell should we be interested in?
2p.
And that's right, because that's the one where the electron's going to be pulled from. So for oxygen, how many electrons in that 2p?
4.
4. 1, 2, 3, 4. For neon, same one, right? How many unpaired electrons are in neon? Sorry, not neon, nitrogen. How many unpaired electrons are in an atom of nitrogen?
There'd be 3 unpaired.
That's right. How many unpaired electrons in nitrogen? And the answer is 3, right? Very good. So, which one of these situations would it be harder to remove an electron from? Nitrogen or oxygen?
It'd be harder to remove it from nitrogen.
That's right. Now, we already kind of knew that because we see that the energy is higher here than there. But what's our explanation for why it's harder to remove an electron from nitrogen than it is from oxygen, Sarah?
It's
nitrogen.
Say that again, sorry.
The
the nitrogen is more stable
than the
than the
oxygen.
oxygen.
Yep. Now, why is it? What's our verbiage for explaining why it's more stable? I mean, we
I'm
say
not sure.
oxygen has an electron, a fourth electron in a 2p subshell, so that when removing that electron, we end up with a half-filled subshell, which provides a degree of stability. Whereas nitrogen, to remove an electron from its half-filled subshell, it's harder because it has a degree of stability already. All right? Does that make sense, Sarah?
Yeah,
Yeah, that makes sense.
Okay. Does anybody have any questions about that?
I have
I have a question.
Yeah.
For the fluorine and neon example.
Yeah?
Well,
You said it like increases like in energy as you move right.
It
Takes more energy as you go right
on
on the periodic table, right?
Well, we see that there's a general trend that way, but you see that there's these dips.
Sometimes
You see that there's these dips in here, right?
Okay.
Is that what you mean? Is that what you're talking about, Chloe?
Yeah, because then that example is opposite. But now I see that.
Right. So nitrogen and oxygen, there's this dip here. It becomes less pronounced as we move down the periodic table. Why do you think it becomes less pronounced as we move down the table? Whose turn is it? Who has their microphone on? Aisha, any ideas why this bumpiness becomes less pronounced as we move down the periodic table?
Is it because there's more electrons now and then losing one, it will be okay? Like
That's right. That's right. That's exactly right. So for example, looking from indium to xenon, this little trend here, removing electrons from this subshell, and Alyssa, what subshell am I pointing at here? Which subshell is that? Indium to xenon. Can you see it all right, Alyssa? Indium to xenon is what subshell? Whoops, where's it at? Here it is. Anastasia, I can't hear Alyssa. Maybe you could write it on there, Alyssa. What's our subshell that we're pointing at? Indium to xenon.
She said 4P.
Oh, 4P? Sorry, I didn't hear it. We're actually at...
Well, her microphone's not working. I said it for her.
Okay. So we're actually at what? Not 4P, but where are we? 1, 2, 3, 4. So it's 5P. Okay. So if we're at 5P, and let's think about the electron configuration for indium, right? We have below 5P all these 4 Ds and then the 5 S's, right? And so we have all these electrons underneath such that the amount of energy to remove an electron from antimony and tellurium is very, very similar to each other. Okay. Successive ionization energies. Removing a second, a third, a fourth electron, so forth, right? If you look at fluorine, and this is measuring how much energy it takes to remove that electron. So it takes energy to remove a first electron. It takes energy to remove a second, more than the first, obviously, and third, and so forth. But then there's a huge, and there's an increase, a gradual increase as you remove the first, second, third, fourth, fifth, sixth, seventh. But then there's a huge increase from the 7th to the 8th for fluorine. If you look at oxygen, you can remove 1, 2, 3, 4, 5, 6 electrons, but then when you try to remove a 7th electron from oxygen, there's a huge increase. Nitrogen, a huge increase at the 6th electron. Carbon at the 5th. Boron at the 4th. All right? So there's these huge jumps in energy when, I don't know, can you see why, Brielle? Why is there this huge jump in amount of energy to remove electrons at certain points? Any ideas?
Is it because those are the numbers where it almost hits like a noble gas?
That's right. It goes into its noble gas core. So, for example, if I write the electron configuration for beryllium, all right? Beryllium, 1s2, 2s, where are we at? 2s2, there we go. 1s2, 2s2 for beryllium. So there's 2 electrons, which are its, what do we call those electrons there, Camilla? What do we call the electrons with the highest N value? Camilla?
So there's valence electrons?
That's right, valence electrons. So the valence electrons, they take energy to remove, but compared to after those are removed, trying to remove electrons from the noble gas core, it takes a lot more energy. Fluorine, electron configuration, 1s2, 2s2, 2p5, right? These 5 electrons can be removed, and then those 2, right? They increase in the amount of energy it takes, but then when you try to start to remove into the noble gas core, it requires a lot more energy. All right? So successive electron successive ionization energy increase as you get closer, or as you get closer to the noble gas core, and then when you try to go into the noble gas core, there's a drastic increase. All right, and we saw this irregularity in going from nitrogen to oxygen, and we explained it by recognizing that when you are removing an electron from the 2p of nitrogen, right, it ruins your half-filled subshell, whereas if you remove an electron from a 2p of oxygen, it actually results in a half-filled subshell, providing a little bit of stability. So the ionization energy is less for oxygen than it is for nitrogen. All right, the opposite of ionization energy is what we call electron affinity. The opposite of ionization energy is electron affinity, and it's the energy associated with an atom gaining an electron. All right? Now, what do you guys think? If we go back to our family model where we said, hey, you have an atom, you have all of its electrons, every atom is going to get mad if you take an electron away. It's going to raise the energy of the situation. What do you think in terms of electron affinity? If you have a family and they say, hey, will you take one more kid? Do you think that the family's going to go crazy if it's asked to take one more kid, Camille?
I mean, there might be some issues, but probably not.
That's right. Every family could take one more electron. And that's right. That if you give an electron to an atom, it doesn't require energy. In fact, for every time you give an atom an electron, it actually releases energy. It stabilizes the situation at least a little bit, sometimes more than others, but always, no matter what, every family will always take one child. However, subsequent electrons always require energy. So if you say, you took cousin so-and-so's kid, that was really nice. Now can you take cousin so-and-so's kid? No, that takes a little more energy. So we'll take it, but it's going to destabilize the situation a little bit. Okay, so that model kind of helps us remember that electron affinities, now the word affinity means, how much attraction do I have to something? Some people say, I have an affinity for chocolate or something like that, right? I'm really attracted to chocolate. So electron affinities are energies associated with taking an electron. Everybody will take one. It'll stabilize their system a little bit. The energy will go down, but the second one always requires energy. So, for example, here's oxygen, gets an electron, forms this, negative 141. Negative 141. Do you remember that chance? What does the negative mean in the negative 141?
That mean that the initial was more than the after energy.
Yeah, very good. That's right. So if we look at a little energy diagram here, right, that the final state was lower than the initial, so energy was released in the process, so gaining that electron stabilized that system. But the second electron, taking an O minus and getting a second electron, what does that mean there in terms of energy, Chloe?
It required energy.
Yeah, it requires a lot of energy to take that second electron. Very good. So, our trends in electron affinity, the amount of energy it requires to gain an electron, electron affinity, the amount of energy that is released upon gaining an electron, follows this trend, all right? It increases as you go to the right, and electron affinity energies increase, as you go up to the top, and then increase as you go to the right. So increasing as you go up and to the right. All right, so, yeah, go ahead. Alyssa, did you have a question or no? Okay. Let's see here then. When we say this is an increase, it's increasing as an exothermic value from left to right and increasing from bottom to top. So if we look at our periodic table, it means that if francium gets an electron, its energy, now if francium takes an electron, who are we at? Daisy? Was that where we're at? Daisy? If francium gets an electron, is that going to release or require energy?
Well, you just said that it increases energy from left to right, so it's gonna not take as much energy since it's on the left.
Okay, but I mean, just if we just look at a single atom of cesium or these ones, any atom, if I give it an electron, is it going to require energy or is it going to release energy when I give that atom or electron to cesium?
My guess is release.
That's right. It releases energy. It stabilizes. Now, if I compare cesium to lithium, if I give lithium an atom or electron, first of all, Daisy, giving an electron to lithium, is that going to stabilize lithium or is that going to require energy to give an electron to lithium?
Since it's higher, is it going to require energy?
Well, not comparing, just initially just thinking about giving an electron to lithium. What did we say about all these different families? If you give them an electron, does it require or release energy to give them an electron?
It releases energy.
That's right. So if I give an electron to lithium, it will release energy. If I give an electron to cesium, it will release energy. Now let's compare the two. Which one will release more energy? Giving an electron to cesium or giving it to lithium?
Lithium will release more.
That's right. And that arrow, in terms of electron affinity, increasing as you go up, lithium releases more energy. Going to the right here, these elements release the most energy upon receiving an electron. Okay? Very good. We're out of time. We'll have a quick review of this next time, but we're going to move on to Chapter 9 after this point. If you have any questions, you can hang around. Otherwise, we'll meet again on Monday. Are there any questions?